answer for this.
Hmm.
So, following figure shows spectrum of an ideal black body at 4 different temperatures, number of correct statements in the following. So we're given energy distributions over here, and the energy distribution is in a peak like this. Okay. Okay, so we're going to be having wavelength here, and we are going to be having intensity. Now, why am I writing it as intensity and not as energy distribution? Think, tell me why.
Intensity includes its energy per unit area and unit time. So
See, because energy distribution is not a very sensible term there actually. Why? Because energy per photon. Now that you know what a photon means, right? You are not Planck. You don't need to think like what Planck thought, right? This was what is it? Planck's what is it? Black body radiation curve, correct?
yeah,
But why should you think exactly the way Planck thought? You can adjust your scenario here to understand what this truly means over here, what energy distribution truly means. So you know that light exists in the form of photons.
yeah,
You know that energy per photon is going to be given by a formula h into c by lambda. That means if I'm going to be having increasing wavelength, what does that tell me about the energy there?
decreases per photon.
Right. So the energy of the photon is going to be decreasing as you go more and more in terms of wavelength over there. Now, the game here is like this. You're given 4 different values of energy distribution there. So the intensity here is also not a proper thing here. Why? Because when you look at the curve which Planck has gotten there, energy distribution, let's first understand what that means first. The energy distribution, if it was going to be perfectly, let's say, as expected, what's supposed to happen there? If it is following something where the intensity is going to be the same, intensity na number of photons, correct?
Yeah.
So if you say the number of photons and each of them is going to be the same, I should be having a graph which is going to be a proper curve where the peaks will be like this.
Yeah.
Right, it has to be on 1 by x. Right. So if it is going to be 1 by x, the curve should have the peaks of the curve lying on these points here.
Yeah.
Yes or no?
Yes,
If
sir.
intensity is going to be the same, that is intensity is same, na number of photons is same, I should be having a curve like this, y equal to 1 by x curve. But what am I seeing over here? What do we see over here? That curve is shifted. That curve is being followed, but it is being shifted away, correct?
Correct, yes. Yeah.
You can see that the curve is still being followed. You're still having T1 being something where technically it's going to be for lower wavelengths. Right?
Yeah.
T1 ka peak dekho.
Yes, sir.
Where is the peak for T1 there? The graph is looking like this, right?
Yeah.
It's like this. So effectively T1's peak was here, T2 is here, T3 is here, T4 is here. So it is still technically following some sort of a line like that, but it is not following it properly.
Yeah. Yes, sir. Yes.
My guess is it will probably go that way. I mean, I've not drawn it properly, but I think you can see the general trend it's supposed to be following. It's supposed to go like this.
Yeah. Yes.
Now, the idea here is if it is going to be following a curve like that, it is basically shifting out slightly. What does that tell you here? What can you understand from it here?
Like, right.
It basically means
There's some
you're not getting the same intensity.
Yeah.
If you are getting the same intensity, it should have followed y by x.
Yes, sir.
You're not getting the same intensity, you're getting different intensities. That means some photons of wavelength are coming out more and more and more. Okay, let us now have a look here. So this is going to be talking at 4 different temperatures, correct? So if you're going to be looking at 4 different temperatures, this is at T1. temperature T1, T2, T3, and T4. Okay. So we're going to be given four different temperatures, four different types of scenarios are given here. So they're asking us which one is going to be the highest temperature here. T1 or T2 or T3 or T4. Now, when you're going to be having something like this, the idea here is how should you proceed over here? The easiest way to proceed here is you look at the peak. The peak is going to be corresponding to a particular wavelength. And usually the peak is also going to be corresponding to the maximum intensity as well, right?
Yeah.
If you're going to be having energy distribution as a scenario here, the peak over here should correspond to both what is going to be the intensity and generally the wavelength which is going to be obtained at that intensity. So if you look at the highest wavelengths which are being seen here, what you should notice over there is
Lowest energy distribution.
it is going to be decreasing.
Mm.
My lines are not proper, but
Mm.
it's supposed to be properly in that direction. T1, T2, T3, T4, you're supposed to be having what to say wavelength decreasing, but at the same time you're also going to be having intensity increasing for that. That means temperature T1 should be the hottest. For instance, if you're, let's say I'm going to be taking a tawa and I want to stick it in the on a stove. If I stick a tawa on the stove, what will happen there?
You get heated.
What will be happening? The tawa will keep getting hot.
Yes.
As the tawa gets hot, what types of hot will it keep getting? It will start off with something like, say, red heat.
Red.
Then it will start going into white and then finally blue.
Yeah.
Something of that sort, at least. So
Yes.
basically, it's going to be decreasing its wavelength, which is going to be shining brightest.
Yeah.
That is, the intensity is going to be talking about which one is going to be shining brightest over there. Is that logical?
Yes.
So the intensity talks about which one is going to be shining the brightest. Fair. But at the same time, the wavelength is going to be something which is going to be telling how much energy is thrown out. The lower the energy of the lower the wavelength over there, the greater the total amount of energy which is getting thrown out over there, which means the object is hotter.
Yes.
Only when it is hotter, it has got more extra energy to throw out, which is why it's going to be throwing out more energy there, right?
Mm.
So that is basically how you basically proceed to check out that particular thing. Which means in this case here, when it comes to the heat of the objects over here, the temperature at which they are present, T1 is going to be greater compared to T2, compared to T3, compared to T4. That is going to be your case over here.
Okay.
Now, so in this case here, option A is unfortunately wrong.
Yeah.
They're asking number of correct statements. So option A is wrong. Let's look at option B. Option B, the black body consists of particles performing simple harmonic motion. Of course, every object is going to be consisting of particles which are performing simple harmonic motion. So this is of course going to be true.
That's
C,
it.
we're going to be having the peak of the spectrum shifts to shorter wavelength as temperature increases. Of course, correct.
Yeah.
That's what we just discussed right now.
Yes, sir.
So this is going to be correct as well. D, we're going to be having T1 by V1. V here I'm assuming is not really V but frequency, correct?
Frequency. I see.
Is equal to T2 by V2 is equal to T3 by V3. What does that tell?
Inversely proportional.
Yep.
I mean,
No, not really. But what is T there?
lambda.
T is signifying total energy dumped. Correct?
Yeah.
Energy distribution. Look. So the T is signifying total energy dump. So if I'm talking about T1 or T2 or T3 or T4, that is total energy distribution. Total max peak energy distribution.
Yeah.
This means this is going to be hc by lambda into the maximum number of or the intensity which corresponds to maximum photons, correct?
Yes.
So this has to be hc by whatever lambda multiplied by whatever is going to be my number of photons for max intensity. That is basically what this is going to be. So in this particular case here, let's now look at what is going to be T by nu. So C by lambda is nu, correct? So I'm going to be having this as h into nu multiplied by this number of photons aspect here, which I'm going to call as n.
Yeah.
So if I'm going to be taking this is my t here, correct? So if I divide this divided by nu and nu will cancel,
Yeah.
meaning I will now be having T1 by nu1 being equal to what here? It will work out as h into peak of intensity n, number of photons associated with that for nu1.
Hmm.
Correct?
Yeah.
And that is basically what it's going to be for each of the other cases as well. So it's going to be giving me some way of measuring the number of photons.
Okay.
This is going to be a type of measure for number of photons. Or you can think of it as number of individual light particles. Don't think of it as a photon. Now go back to how, what to say, Planck should have thought of this, because it's black body radiation, correct?
Hmm.
So at that time, Planck did not know what was a photon,
Yeah.
because Planck was the first dude who defined a photon, correct?
Yeah. Yes, sir.
So now you start thinking, break down, this is what we think of it, exactly
Hmm.
speaking now.
Yeah.
So now you revert back to what Planck thought of this particular thing as. This was what he thought of as type of measure for number of light particles. For number of light particles. Which is why this is going to be very fundamentally brilliant thing. Why? Because this talks about the number of particles of light in each case,
Hmm.
number of pieces of light. So if the intensity was the same in each of those cases, all of them are going to be the same. That is this n over here, which is going to be number of photons for max intensity. If that is going to be the same, then you'll be having the same value for sure. That's the idea here. So
Hmm.
option Delhi, I have no idea. My guess is he would have maintained same intensity. If he had not maintained same intensity, this would not have made a meaningful observation over there. So he would have tried to have maintained same intensity. So most probably that Delhi would have been correct over here according to Planck's measurement, depending on what he did there. Mostly this is going to be experimental circumstance.
Sir, but then there's like in physics we learned that there's Wien's displacement law, right? So that
I do
says
not
that,
know that laws. You tell me the graph for it, then we'll talk.
so it's not like it's like lambda max into t is constant always.
Lambda max.
Into t is equal to b.
Lambda max is going to be the wavelength of the substance emitted maximum.
Yes, sir. Yeah.
Okay, into
T temperature at that of that
that will
point.
not be sensible. That is not a correct law. That is something which is not something doesn't click over there. That is probably an approximation.
1 second.
Confirm if
Yes,
it
sir.
is perfectly correct.
Lambda max
Approximation.
wavelength peak is equal to into absolute temperature is equal to constant.
Give me the exact thing. Lambda max into.
T is equal to b. Lambda max is wavelength peak and T is absolute temperature.
That's what I'm trying to say. There is no lambda max meaningfully. Think for a second. Think for a second. Is this making sense? Is it?
Lambda at maximum,
That's what I'm trying to say. This is not correct. Anyway, give me the full statement. I will prove it to you. Give me the full statement. Lambda max into T is equal to
constant b.
constant B.
Yeah.
Now, this is something which is absolutely for sure an approximation. Now, why am I saying this is a random approximation and is meaningless? Which is probably why we do not study this in chemistry. Lambda max. What do you think lambda max is going to be? What is the definition of lambda max? Go into it.
The
The
wavelength.
maximum wavelength we can observe.
No, I think it's the wavelength peak, right?
Okay, so this is not the wavelength. This is a peak wavelength. That is a
Yeah.
T1
At
wala
the
wavelength.
top, yeah, exactly. That's a,
Oh, okay. That is a fair assessment. Then it is acceptable. Then it is
but
a fair.
then so then shouldn't T by mu be
No, this is an
constant?
experimental condition then. This is an experimental condition. That's all. This will probably bring up the same factor that intensity is going to be roughly the same. Basically, if you're going to be having this now, what does this tell you? T by nu is going to be a constant. T by nu is going to be basically number of photons for maximum intensity, correct?
Hmm.
I'm saying this is the same thing. These are same.
But then we don't know whether n is same for all these,
Stop,
right?
stop, stop. Don't argue right now. I've already thought it through. If you want to argue, you mathematically argue. Don't give me some random shit. Now, what does this basically mean if it's going to be a constant? What did I get over here? We got T by nu will be equal to what?
Measure of particles.
So T by nu is going to be H into number, correct?
With
Where this
constant.
N, what does this stand for? This stands for number of photons
Light particle.
of light,
Hmm.
right? This is what I'm talking about as intensity come measure, basically a number of photons of light which are going to be present over there. Now break it down. What is this T into lambda max? This nu is corresponding to that maximum frequency thing there, correct?
Yeah. Yes.
Wavelength scenario there. So if this is going to be the case here, I can effectively write T is going to be some constant divided by this particular lambda,
Hmm.
right?
Yeah.
Now, what is nu?
C by lambda.
C by lambda. So I'll be
Hmm.
getting this as T divided by C multiplied by the same lambda nonsense here.
Yes. Yeah.
I'm going to be having H into N. I'll just take the C over here and multiply it over here. What do I get then? The
Same thing.
lambda into T is going to be HC multiplied by my N.
Hmm.
Basically, they're calling it some constant over here. I'm telling you what that constant is going to be. That constant is going to be HC into N. You understand what I'm trying to explain here?
Hmm.
That is, this is same as my lambda, as the lambda max which you mentioned, correct or not?
Yes, sir. Yeah. Correct.
So this lambda max into T actually works out as Hc into this N over here, which talks about number of photons of light. Now, instead of calling it as Hc into N, what did they call it over there? They called it as a new constant. What was the constant they called it over there?
B.
Tell ya.
B. Bombay.
Okay, so this is going to be called as P. So this is an experimental constant. This is not going to be something which is going to be anything else. So it's an
So then,
experimental constant.
and
Depending on how you plan your experiment, you can maintain this a constant.
no, sir. There's a value for that.
That's what I'm trying to say. This would have
Hmm.
been something which could have been controlled in an experiment. I'm
Hmm.
saying that in the paper they published over there, they would have used it as a constant over there, which is going to be involving the maximum intensity which you can observe at that time.
By
Remember,
fixing it.
matters. Think, think for a second here. This is
Okay.
done at a much, much earlier time.
Yeah.
This is not really a constant. This B here is not really a constant. It is a constant based on the experimental conditions which were available at that time. Not
Correct.
anymore. I'm 100% sure we've got better systems where we can fire up lasers which are going to be producing much higher intensities. You agree this is independent on number of photons of light?
Yes.
If
Yeah.
I can plot a larger number of photons, obviously I'll be able to get a larger value of
Greater
B.
constant. Yeah.
So this is not really something which is going to be a meaningful observation, but it is an observation which will be holding good mostly when it comes to a particular small band of wavelengths. My guess is in the visible region. Not 100% sure in which region they were experimenting on. This
Yeah. I
is
think visible reason.
the
Like
constant.
visible
Basically,
reason.
you can control the number of photons. That's the idea. And you know that it is going to be a constant. That's the game here. So if you can
Hmm.
keep the number of photons a constant over here, then you will end up having this particular what equation? T by nu is going to be a constant there.
So this is only for visible light
I do not
region.
know. I do
I
not
mean,
know.
it
It
is
depends
on
on that.
Google.
Huh?
On Google, it shows that the peak is only in visible light region.
Well, I do not know the reason why it is a constant, but I can make a guess as to why it is a constant and when it will be a constant. Your science is solid. It doesn't matter whether you know the experiment's name and shit and whatnot. You just need to know the data which is going to be produced over there. So I'm
Hmm.
guessing this is working only for what to say visible region, correct?
I think so.
That's what Google is mentioning, is it?
I mean, they just gave the constant lambda peak is equal to, but then they gave peak to be like other places as well. Uh,
It'll work for a particular range, I do not know which range they were working on. It would definitely include visible. It might
hmm.
include a few of the other parts also, because remember, those guys are working on UV also at that time and a little bit of IR also. As the wavelength becomes larger and larger, it becomes more difficult to measure. IR would have been more complicated. But UV, though, I wouldn't be surprised if they were using UV also there. Anyway, this is basically going to be having a particular spectral range within which only it will be working. It is not a proper constant. It is going to be an approximation. Anyway, coming back to the last option there, the given spectrum could be explained using quantization of energy. Yes, the given spectrum could be explained using
That's what.
quantization of energy, absolutely.
Yeah.
So for the question here, E will be correct here. D is also correct here. So four options are correct. What is the answer given?
Answer given two, sir.
Two.
Yeah.
Let's have a look at the options there. A is gone there. Black body consists of particles performing simple harmonic motion. Peak of the spectrum shifts to shorter wavelength as temperature increases. That is fine. T1 by nu 1, T2 by nu 2, T3 by nu 3. Question is what is nu, what is nu 1, nu 2, nu 3? I'm assuming it is going to be the same as that. In that case, it should be the same. Okay. Black body consists of particles performing simple harmonic motion. Even if we assume that they are not going to be considering it that way, technically, let's assume they are going to be considering it as electrons getting excited and de-excited. If we do it like that, then it is still going to be okay. We can neglect B, but it still gives answer as 3.
I'll just see the mains people.
This is a JEE mains question.
Yes, sir. Yeah.
Which years?
23.
23. Okay. What is the answer for it, dude?
Just a second, sir.
You know which paper also?
Yes, sir. Yeah.
Very nice. Good. The ground state energy of hydrogen atom is minus 13.6 eV. Consider an electronic state psi of helium plus, whose energy azimuthal quantum number and magnetic quantum number are so and so. Which of the following statements is not true for the state psi? Okay. So the ground state energy is given. Consider this as the state of helium plus, whose energy azimuthal quantum number, magnetic quantum number. Okay. All right. Now, using the data given here, we'll have to basically figure out what is the idea there. Delhi is going to be the nuclear charge experienced by the electron. In this state is less than 2 electrons, where E is the magnitude of the electric charge. Now, this is a very shitty option, Delhi here. That is based on something which is a very useless option. But since it has been asked, not even sure whether it's a correct paper or not. But let's check it out. So that is going to be based on what is called as Slater's rule. But let's have a
I
look at
see.
the options here and find out what else is applicable here. So firstly, you're going to be having ground state energy of hydrogen atom is given as minus 13.6 eV. And they're giving you, they're asking you psi of helium plus. Okay. Energy is given as 3.4. So if the energy is given as minus 3.4, for helium plus, it's going to be Z squared by N squared. So it's minus
N is equal to 4.
13.6 into 2 squared divided by N squared. This is going to
Equal
be minus
to
0.4. So we're going to be having N here
4.
mostly has to be 4. So you're going to be having N equal to 4 in this case. So if N is going to be equal to 4, we're going to be having shell number 4 here. So N is equal to 4. They are telling us that azimuthal quantum number L is going to be equal to 2 and magnetic quantum number M is going to be equal to 0. Okay. So it is going to be L equal to 0 is going to be your S subshell. L equal to 1 is going to be your P subshell. L equal to 2 is going to be your D subshell. And 0 is basically going to be standing for Z
Something.
square.
Oh.
So we're going to be having in this particular case here,
Sir, is
uh,
that just convention or like?
convention.
Okay.
So 4dz squared. This is going to be the orbital which you're going to be considering in this particular case here. And they're asking us more information here. First off, two angular nodes. Yes, you're going to be having two angular
Any.
nodes. They're both going to be two angular cones, not angular nodes in the conventional sense.
Cool.
So you'll have two angular nodes, that is correct here, but they are going to be angular cones.
Yeah.
Next is going to be, it has three radial nodes. That is going to be wrong over here. You're going to be having 4D over here, having only one radial node.
Yeah.
And you're going to be having 4D state, quite obviously. Nuclear charge experienced by the electron in this state is less than 2 electrons, where E is the magnitude of electronic charge. This is true, technically speaking, because it is going to be in the D subshell, well shielded. Oh, no, no, no.
Mm.
It is not that well shielded. But it is going to be having 3D, which is going to be bad shielding before it. 4D ke liye, which are the shielders are? Shielders are going to be S and P. Ah, they are good shielding only. So this might be true. This might be true. So good shielding. Why is it going to be having good shielding? Mainly because the shielding provided for the 4D is going to be coming from 4S and 4P. Not 4P, sorry. 4S and 3P. The two orbitals are filled up just before it. 3P, yeah, 3D, 3D, 4S, 3D. Okay, let me just put the dam down. Then it'll be easier for me to pull it up properly.
The diagram.
It'll be 4P and 5S. Correct. Now better. So only 4P and 5S are providing shielding for this, and they are going to be providing good shielding. What is the answer given here?
That's
So
wrong, sir.
good shielding, then Delhi should be correct here.
Oh no, it's given wrong.
Given wrong, huh?
Yeah.
Then we'll have to basically figure out why it's given wrong here now.
Yeah.
Technically speaking, 4D ke liye, the shielding has to be 4P and 5S. They should
Sir,
be
why
good.
aren't you considering anything else?
Sorry, repeat again.
Why aren't you considering any other? Oh, Slater rule.
Not necessarily Slater's rule, da.
Then
Forget about whether it is Slater's rule or what. The game here is what is providing shielding, right? Because if the shielding is going to be stronger, then it is going to be experiencing slightly lesser magnitude of the what to say effect, right? If the
yeah.
shielding is going to be weaker, it should be experiencing more magnitude of the attraction. That's the idea over there, which is why we end up saying that after the D subshell is filled in, you're going to be having a small size contraction being seen, right? Similarly, after the F subshell is filled up, we get a small size contraction after that as well. So that is the basic rules to basically follow. Now, the question here is going to be whether we take it as it is going to be experiencing more attraction because of shielding. I mean, more attraction because of poor shielding. Meaning, is it going to go above 2 if poor shielding is there? Then this entire statement is meaningless. It becomes wrong. Then the minimum for shielding is going to be 2. Meaning in this case, even though they are having good shielding, I'll say that they are having 2 electrons worth of attraction. But if they are going to be having poor shielding, we can say it has more than 2 electrons worth of attraction. You understand what I'm saying there? So it depends on how you basically look at the convention there.
So like if we assume like suppose a helium atom, not like an ion, then it has 2 electrons in.
Then yes, definitely.
Yeah,
Then yes,
like
definitely. Because
that
a
logic, can you say something?
helium plus will obviously be having more attraction compared to a helium atom. Right.
So then it should be wrong, right?
Then it is going to be wrong for sure then.
In that logic.
From that logic, it is perfectly wrong there. We don't need to bother about it at all. Not bad. That's
So
a
then
good
why?
From that point of view, it is completely wrong. It doesn't make a difference at all which state it is going to be in, what shielding it is going to be in. Because if you
That's
compare it to a helium atom, it definitely is going to be having much smaller size. Why? Because helium plus ion, it's already lost an electron.
yeah.
From that point of view, it is definitely wrong. That's another good way of looking at the entire thing here. If we consider it from a helium atom point of view, absolutely it is going to be experiencing more than what the helium atom is able to throw out. It's already
Okay.
helium plus one ion.
Yes, sir. Yeah.
Okay. All right. Next up. So you've done a fairly thorough analysis of the questions. Not too shabby.
Yes, sir. I sent the next one.
Yeah. The figure below is the
Sir, I was getting like a little, like
one
the
second. Let
answer
me
was a little different than
the
mine.
potential energy versus nuclear internuclear distance of hydrogen molecule in the ground electronic state. Okay, what is the value of net potential energy E naught as indicated in the figure in kilojoules per mole for D is equal to D naught, at which the electron repulsion and nucleus repulsion are absent. Okay, so basically you're going to be separating them by infinite distance technically over here.
Hmm.
And as reference, potential energy can be taken as zero when the electron and nucleus are infinitely far apart. Okay, mark potential energy for the two hydrogen atoms per mole as answer. Okay, per mole as the answer. Okay, figure below is the potential energy versus internuclear distance in a H2 molecule. Okay, what is the value of net potential energy as indicated in the figure in kilojoules per mole E naught? Okay, all right. Net potential energy. Okay, all right. And we are going to be considering the graph from 0 to this perspective. Okay, D equal to D naught. Okay, at which the electron repulsion. Okay, as a reference, the potential energy of hydrogen atom is taken at 0 when the electron and its nucleus are infinitely far apart. Okay, so in this case here, they're asking us what is the potential energy. No, what is the exact question here? As a reference, the potential, what is the net value of net potential energy E naught? Okay,
Total potential energy for two hydrogen atoms
hydrogen atoms
per mole. Yeah.
per mole. In that form where they are going to be, uh, what to say, in the molecular form.
Hmm.
Right, so when you're in the molecular form, they're going to be at the lowest energy level at that particular case. With respect to that, how much is it going to be? So, for instance, if I'm going to be having, say, this is the reference line here. This is going to be giving me my E naught marking here. Okay, I'm going to be having the energy level at this level is going to be zero at infinite distance, and we're going to be having the graph basically going as usual like this. Something like this. Okay,
Yeah.
and we're going to be having this value being asked, and this is going to be for H2 molecule. Okay, all right. Hmm. Okay, and they're telling us D is going to be the distance. Hmm. Okay, all right. So in this particular case here, we're going to be having hydrogen molecule. We are asked over here, two hydrogen atoms are basically interacting. This is also an old JE question, is it?
Yes, sir. Yeah.
Which year is this?
Second.
I would like the actual version itself.
Just a second.
Yeah,
2020, sir. Paper two.
2020 paper two.
Yes, sir.
Okay. So in this here, we are going to be having, this is a full question. Good enough. We'll directly use this photo itself. Okay. So we are given that we are going to be having a hydrogen molecule over here, and we are having interaction happening. And this is going to be for ground state.
Hmm.
Now, when you're going to be talking about a molecule's ground state, what is going to be the lowest energy level for the molecule? This is going to be hydrogen molecule location, correct? Or a ground
Yeah.
state scenario. So what is going to be the distance here? We're going to be having to calculate that particular value out first. So if I consider the hydrogen molecule, H2 molecule, what type of an interaction is it expected to be? It's expected to be a 1s interaction,
Yeah.
correct? So it's supposed to be a 1s sigma 1s. Fair?
Mm.
So if it's going to be a 1s sigma 1s, then in that particular case there, the first shell 1s is going to be, of course, n equal to 1. What is the distance of the electron in this particular case here?
Or not.
0.5 to 9 angstrom,
Yeah.
correct?
Mm.
So you're asking us what is going to be the potential energy of the electrons present at this stage over here, right? At this location here. Potential energy, what is the formula for potential energy?
Minus KQ.
Q2 by R. This is per electron. So we're going to
Positive.
be having two of them here, correct?
Yes, sir.
So we're going to be having, in this particular case here,
2 into
two
N.
electrons. How much? Because each of those two electrons are respectively at a distance R from one of the nucleus. But they are going to be at very large distance to the other nucleus as a general understanding. But that is not the case here, correct? Because both the nucleus electrons are going to be in the same region. That's what ground state they are interacting means, correct?
Mm.
Think for a second what's happening there. We are having a 1s sigma bond being formed over there.
Mm.
So we are going to be having one nucleus present here and one nucleus present here. We'll be having both the electrons present over here. And this distance is going to be 0.529 angstrom. And we'll also be having this distance also as 0.529 angstrom.
Mm.
You understand the idea here clearly? So basically, we are going to be having hydrogen atom number A nucleus.
Yeah.
This is hydrogen atom B nucleus.
Mm.
Fair so far?
Yes, sir. Yeah.
So if this is going to be the case, what will be happening now then? Hmm?
Now the put it'll be KQ and Q2 by 2 into 0.529.
Right? So go for it now then. How should you proceed now then?
Into 2 by 2, it
Having
cancels
K1
the
Q2 by R over here. In that R there, we will end up having,
2A naught.
sorry,
It'll be 2A naught, right?
sorry, 2?
R will be 2A naught. 2 into 0.529.
No,
That's
R
right.
will be the same. R will be the same because the distance is the same. The electrons are going to be at distance of 0.529 only. R is going to be, if you take it as 2A naught, that is going to be distance between the two nuclei. Na?
Yeah, that's what we need to do now.
Why do we need that?
Then why are we not considering the nucleus attractions?
It is not going
Repulsion.
to be because look at what is being taken here. This is going to be electron, at which electron repulsion is absent over there, and nucleus repulsion is absent here. You're going to be assuming that not D for D naught over here. At that point, we are going to be having the perfect level, which is going to be achieved over here, which is going to be at this point here. This is your D equal to D naught point here. But this energy here is for the electrons here, maximum total potential energy for two hydrogen atoms per mole. Oh, they are not asking that way. Potential energy of hydrogen atom is taken as 0 when its electron and nucleus are infinitely apart. Net potential energy.
Sir,
This is
what?
for the entire system only.
Hmm.
Entire system के लिए means we'll have to add and subtract over here. Let's try it out क्या आता है. So we'll end up having two electrons here. For them, the distance is going to be only, what is say, R over here. So nuclear repulsion also we'll have to consider. Electron repulsion also we'll have to consider now. So let's subtract out the nuclear repulsion. What is going to be nuclear repulsion there? That will be again KQ1 Q2 by R. So we'll have
Oh,
K1 into Q2 by R here. In this here, I'll be having Q1 is going to be one electron because it's a nucleus.
Q2 also.
Q2 is going to be two though because there are two electrons present there.
Hmm. Okay.
And R will be 0.529. And this will be with a negative sign. And this will be with a positive sign. Okay.
Into 2, right? Because 2.
Sorry.
Into 2, right?
Why do I need to do into 2 here? Repeat.
There are two hydrogen atoms, and aren't we considering both their attractions with the electrons?
Fair. Into 2. There are 2 nuclei, definitely. Each one is going to be having this attraction as well. So
Again,
attract
with the two.
nuclei 1 with the 2 electrons here is going to be this much.
Uh,
Nucleus 2 with the 2 electrons is going to be this much. Good. Okay, cool. Already into 2. And next is going to be the repulsions there. This is attractions. So it's a negative value. Repulsion wise, you're going to be having nuclear repulsion. We can't talk about electron repulsion because they're in the same orbital. So we are not going to be assuming that part over there. We're going to neglect that there. So nuclear repulsion wise, we'll have K into Q1 into Q2. This will be 1 electron worth charge. This will also be 1 electron worth charge divided by, in this case here, I'll be having 2R.
two are, yes.
Hmm.
This is a repulsion again.
Repulsion.
Minus.
So plus
No,
here.
no, plus, 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 plus.
So net value will work out as how much over here? We'll be having
4
into
by 2, 4 minus by 2.
4K into E squared divided by R naught minus sign के साथ, and this will be plus K E squared divided by 2R naught. Okay, I can write it as this will be K E squared itself. This I'll make it as by 2R naught. Now I'll make it 8. So this works out as
Minus 1 by 2.
minus 7K E squared divided by 2R naught. This works out as 3.5 K E squared by R naught with a negative sign. Per mole में, if I have to calculate, this will work out as multiplied by Avogadro number. It works out as minus 3.5 K E squared R naught multiplied by Avogadro number. Electron value of net potential energy indicated in the diagram. We are talking only for the electron. This is for the entire system. Only for the electron now, it will be just this, which will work out as 4K E squared by R naught. Only for electron if I consider. How do I get there? Only for electron. In that case, it will be 4 into K into E squared by R naught, which works out as multiplied by Avogadro number, of course. So that will work out as much, then it will work out as 4K E squared by R naught. So सब्स्टिट्यूट तो करना पड़ेगा टूडिए, ये सब्स्टिट्यूट करके तो कर सकते हैं,
So, but
cannot be without substituting.
just a second.
Do we have a solution available?
Yes, sir, yeah.
Send me the photo of that. I'll be able to make more sense of it directly.
They didn't consider like one second.
That's what I'm looking at. 2 possibilities here. Now I want to know which one is even working closer. Is it this one or is it this one which is closer? And what are they going with?
Yeah, sent it.
SK Q2 by R, okay. Minus K square potential energy of 1 hydrogen atom in ground state, okay. They're not considering nuclear repulsion here, first of all. And they are taking 1 hydrogen atom in ground state, okay. 2 hydrogen atoms or 1 molecule of hydrogen. Okay. One more thing they are doing here is they are assuming that each of these atoms are just individually in ground state and the electrons are not in the middle. So they are basically not taking it like this. They are considering that each nucleus is only attracted to 1 electron at a time. Doesn't make sense logically. They are only taking 2 individual hydrogen atoms, not in a molecule here. Because if you consider it as a molecule, the 2 electrons should be attracted equally by both the nuclei. That's the idea. Here we are not considering it like that. So what they have done is acceptable over here. from the point of view of if I consider it as two individual hydrogen atoms. Not a molecule. So if I'm considering them as two individual hydrogen atoms and not as a molecule here, then in that particular case, this is all acceptable. So this is going to be meant for at a distance d equal to d naught, which is going to be at this infinite distance. In under that condition, then this is going to be applicable. Let's have a look at the question again. That means I did not read the question properly. What is the value of this? What is the value of net potential energy E naught for D is equal to D naught, at which the electron repulsion? The question is valid only, da. Their answer is also not correct. Actually, not wrong here. Their answer is correct here. I assumed wrong here. I assumed that they wanted at this distance over here, at this point here. That is a mistake I made here. My
They
entire,
wanted D naught.
huh?
They wanted D naught, right?
They wanted D naught.
But then they only give that. It's. I mean,
The rest of the question is nonsense over there. Don't read the remaining part that the reference and all is not meaningful there. The real part of the question which is meaningful over here is what is the value of net potential energy E naught? This E naught value here. Don't care about what is the scale which is taken. There is no scale. All right.
okay,
They're
okay,
asking
okay.
what is that net value E naught at which is you're going to be having inter-electron repulsion is absent and nuclear repulsion is absent. So at this point here, you're going to be having only two individual atoms, only two separate hydrogen atoms.
Won't that be at infinity?
Technically, it is at infinite distance from each other, but you can basically say at ground state independently.
So then why? Oh, okay. I see.
Sorry, what?
Okay, okay, okay. Nothing. Sorry, got it. Got it. I was. Uh,
The idea here is by giving this graph, they're just confused. That's
yeah,
all.
D naught they give. So I was very confused. I thought it was like finite something.
That is not the point at all. The D naught is not a finite,
Oh,
it is just a random infinite distance. They're
yeah.
asking at that what is going to be the case. So when you
Hmm.
treat them as two individual hydrogen atoms, not a molecule, at distance D equal to D naught, technically infinite distance.
Hmm. Okay.
Effectively,
Then
what
that
is
makes
going to be
sense.
happening here? You're going to be having no electron repulsion and no nuclear repulsion as well.
Only two nuclears and electron repulsion attractions.
Yes, correct. Huh? So basically treat them bluntly as individual species over there. So when you treat them as two individual atoms,
Multiply by two again.
none of this nonsense applies. This is for the molecule.
Hmm.
This is for molecule assuming ground state. Is 1s. But we don't need to do any of that assumption. It's a much simpler thing. They're asking only for the individual atoms over there. So very straightforward, get it done. For the molecule, if you end up assuming what to say, this particular type of conditionality, then whatever we did applies over there. This is going
Hmm.
to be for the nuclear repulsion. There should be one more aspect which has to be added in for the electron repulsion also.
Hmm. But then we neglected that.
We neglected that in this case here.
But then the you know.
This is electron nucleus attraction, correct?
Yes, sir.
We neglected electron repulsion because that is going to be something which I assume would be taken in the Pauli's exclusion principle anyway. So
Oh.
that's basically the idea here. So if we are going to be considering them as individual atoms, then whatever they have done perfectly applies. It will simply be very straightforward. If you take them as individual atoms, it will be minus k e squared by r naught
Hmm.
per hydrogen atom.
Yeah. Per hydrogen atom. Yes.
That's it. So you're going to be having two separate atoms over there, implies 2 times minus k e squared by r squared, by r naught.
Hmm. Okay. Yeah. Got it.
Two hydrogen atoms.
That's the answer.
No.
Into it.
And if you want to convert it into what to say the
Moles.
per mole type of thing, all you have to do is multiply it by
Yeah.
molecular see Avogadro number.
Yeah.
Fairly straightforward.
Okay. Yeah.
You understood the idea here?
Yes, sir. Hmm.
I was stupid enough to go for a much more complicated case, but yeah,
Yes, sir.
mistakes are mistakes.
Yes, sir. So like in this paper, I just saw like another question.
Mhm.
Like I think this is chemical bonding. Here, do you have to like memorize the ionization enthalpies of like
What's the
you
question?
know sir, do you have the paper open? Or
I am about to download it. Tell me the question.
sir, it's like the first, second, and third ionization enthalpies I1, I2, I3 of four atoms with
Question number, I'm
atomic
having the J Advanced paper open in J Advanced website. Question number
2020 paper. First question, sir, for me.
2020, first one. Okay. IE values. Okay.
Oh yeah,
First, second,
yes,
and third IE values are I1, I2, I3 of four atoms. The atomic numbers n, n plus 1, n plus 2, n plus 3, where n is less than 10. Are tabulated below. What is the value of n? Okay. Why do you need that? You need to just guess.
yes,
Look at it. N plus 3 la kya ho raha hai? You're going to be having that being something where the ionization energy is increasing after the second one
yeah.
dramatically. That means that's group 2. N plus 2
Oh, okay, okay, okay. I remember now. Okay, okay.
n plus 2 is your group 1 because
Uh,
I value is going to be much higher after the first one.
yes.
The first
Okay,
one is
okay.
lost very easily. Second one is lost much more difficultly,
Okay, yeah, now I remember. Yes, sir.
much
Got
more
it.
difficultly. So that is group 1.
Yes.
So use that kind of common sense and apply.
Oh yeah, my bad. Yes, sir. Yeah.
So n plus 1 is what? Noble gas already.
N plus one.
N
Yeah.
plus 2 is group 1. N plus
N
3
plus
is
two
group
should be
2.
11.
So n plus 1 is your noble gas.
Yeah.
So n is
Yeah.
10. See, n is 9.
N
Or
is
n
9.
can
Yes.
be 2. N can be 1.
N can be 1.
Yeah, n can be 1 also. Right. But the problem there is if n is 1,
N is 1,
then
then
I
the
can't
first.
lose 3 electrons.
Exactly. Yeah.
So
Yeah.
n is not going to be 1. So n has to be 9 in this case.
9. Yeah. Okay. I was just wondering. Okay. Hmm.
You understood the method there?
Ah, yes, sir. Yeah. I just.
Okay. Anything else to discuss in this paper here?
I didn't think a few of these questions came in our paper once. Hmm. Sir, I had like a general question.
Okay.
Sir, like, how do you solve like a Schrodinger's wave equation? Like, how does it, like, what does it mean to solve?
Mm, what are you really asking?
Like, uh, sir,
What does it
Schrodinger.
mean to solve the equation?
Ah, yes, sir. Like, we get like the wave function, right? Like,
What
um,
do you understand by Schrödinger's equation so far? Let's go there first.
so it basically tells us about the like the information about like the electron. I mean, like,
Okay, so let's start off with the analogy first. So you were cooped up in a particular place during your COVID time.
hmm,
Okay, so basically, look at your entire duration of your COVID time with your house in a map form. You are a dot in that house. Okay,
hmm,
now I want you to think of your entire COVID time. You are the dot which is present in the house. So if you're going to be sitting in your spot here, you're going to be sitting in that spot. You'll be seeing a God's eye view. The map will be basically like a 2D map which you're seeing.
hmm,
Now, your entire COVID period, bring it down into a video of 2 minutes, represented like that. What will you be? You'll be a dot which is like moving constantly here and there,
hmm,
right?
yeah,
Now, I want you to try to understand that mathematically. What are you? You're a constantly moving object,
Hmm.
constantly moving dot. The way to depict you is like some kind of a wave.
Hmm.
Because I don't know where you are stopping, etc. I can't stop you at a particular instant.
Yeah.
So I'm going to be looking at you as a wave right now. So when I look at you as a wave, there will be some equation associated with you.
Yeah.
So how do I study you as a wave now?
Wait, sir. You said there'll be a equation associated with, what do you
Associated
mean?
with that wave, which is moving constantly. It is a point which is moving constantly, correct?
Yeah. Yes, sir.
I can depict that by some equation.
Like the path it follows, like that.
Whatever, I don't care what it is. Mathematically, I can depict it if I set a set of parameters, right?
Yeah.
Like for instance, in your house, if I give you a house set of dimensions,
Hmm.
I can then start representing you with a point over there as a particular point which is there in the 2D. I can then represent you as a wave, correct or not?
Yeah.
As some mathematical equation, I don't care what equation, but some equation is applicable. Yes,
Hmm.
that equation is your wave equation. That is the equation which is you as a wave. That is you as a matter wave.
Gives
Now, if I
location.
want to study you as a matter wave inside this unknown space called your house, for me it's an unknown space, correct?
Hmm.
I will break down your house into pieces.
Yeah.
And then I will study your wave-like nature or that equation which represents you in each of those places.
Hmm.
That is literally what we are doing when it comes to the atom and when it comes to the electron inside the atom. So what is the Schrodinger's wave equation? Schrodinger's equation basically talks about electron as a wave. What does it mean when I say we're going to be taking the electron as a wave here? The electron is the object which we cannot isolate and say it is present here. It is not a particle anymore. I cannot
Hmm.
say where the electron is. I can never find the electron. It is a constantly moving object.
Hmm.
So when it is a constantly moving object, I only know the path it is basically or where all it has been done because of the effects it has left on the field which I can sense. I can sense the electric field.
Yeah.
I can sense the magnetic field. So based on those fields and the effects the electron leaves, I can sense that it was there, or it should have been there, or it probably was there, something of that sort. I cannot tell where the electron is ever going to be. So I'm going to consider the electron as a pure wave now. So the electron is a wave. We have what is called as a very famous thing called as standing waves in physics.
Hmm.
Let's quickly talk about what is a standing wave. So if I'm going to be having, say, this is a wall here. Let's say I'm attaching a string on this wall here, and I make waves on it.
Hmm.
That is called a standing wave. What is the speciality of a standing wave? If the thread is present over here and I'm making waves on it, the
It's,
idea
it's,
there is
it's
very
more.
simple. In that, I'm going to be having the wave is going to be bound within the space of the thread.
Okay.
Right. So
Hmm.
basically, I'm going to be having my hand over here as a thing here. If I'm having a string here, I'll make a wave. The wave will travel. It will hit this wall. It will rebound back,
Hmm.
opposite angle, phase change ke saath, and it will be present in the same wave. So this direction wave and the opposite direction wave are all in that same string only.
Hmm.
So because the wave which is moving this way is also bounding back, it will both interfere with itself constructively and
And
destructively,
yes.
creating your nodes and antinodes.
Yeah.
You've learned about that, correct?
Yes, sir. Yeah.
This is a typical standing wave. But this is a typical standing wave in one dimension.
Sir, but then want all.
Let's not go there. You understand till what I've talked over here,
Yes,
yes?
sir. Yeah. Hmm.
So this is a typical standing wave in one dimension. Now, standing waves in one dimension have a very famous equation in physics called the standing wave equation, which is a double differential equation which applies to all standing waves in one dimension. When I say applies, I mean it works at all for all standing waves in one dimension. That equation is going to be something like this. Uh, if I take psi, or rather, let's say I'm talking about y is equal to f of x as my standing wave in one dimension.
Hmm.
Okay, the equation of the wave is y equal to f of x. X is my amplitude
Yeah.
in one dimension. Y is my equation of the wave itself.
Hmm.
Okay.
Hmm.
What is going to be happening now is this y equal to f of x over here. I'm now going to be double differentiating it. It will become d square y by dx square.
Hmm.
Differentiating it, of course, with respect to the only variable I have x.
Hmm.
This is going to be equal to minus 4 pi squared by lambda squared into f of x. This is called as your standing wave equation.
Hmm.
This is a double differential equation, as you can quite clearly see, which is going to be applicable for all standing waves.
Okay.
You can
Hmm.
test it. Please do so. The
Yes.
physics testing, I'm not going to be going there. Use it and test it out. The physics equation called standing wave equation, it applies for all standing waves in one dimension. Schrödinger now mimicked the same model. What was the mimicking he did? He took that the wall is the same as your, what to say, nucleus. The electron is the wave itself.
Hmm.
And it is bound inside the space called the atom. You understand the idea here?
Hmm.
So I'm going to be having a three-dimensional space now, where I'm having a wall present in the center. That wall is extremely heavy, and you're going to be having a string which is going to be attached over there, which is obviously going to be present as a wave now. That wave is my electron itself.
Hmm.
So in this case here, I had a wall, I had a thread attached, I had myself making waves on the thread, correct? So what was the force holding the thread to the wall in this standing wave which we talked about? This was tension force.
Tension.
So I had tension force here.
Here we have
Instead of tension force, what will I be having?
Coulombic.
Electrostatic,
Yeah, Coulombic.
Coulombic.
Hmm.
And here it was one dimension in the first place over here. Here the electron is going to be in a three-dimensional space over there,
Three-dimensional
so
space.
3 dimensions. So I'll be extrapolating this equation to 3D. When you extrapolate that equation to 3D, the equation becomes, instead of d square, it will become dou square. And in this case here, instead of writing it as y equal to f of x, I'll be writing it as a new equation over here. Psi is equal to f of x
X,
comma
Y, Z.
y comma z.
Hmm. Yeah.
Okay, so I'll be having dou square psi divided by dou x squared plus dou square psi divided by dou y squared plus dou square psi divided by dou z squared.
Hmm.
This is my
Minus.
triple double differential for the entire thing. This entire nonsense, I'm going to call it as del squared psi now.
Hmm.
Capital del squared psi.
Yeah.
This is supposed to be equal to minus 4
4
pi
pi.
squared by lambda squared into f of x. But instead of f of x, what do I have here?
Psi.
I have psi.
Hmm. Okay. Yeah.
So far clear?
Yes, sir.
So now this will basically work out as del square psi is equal to minus 4 pi squared by lambda squared. This is going to be the electron itself as a wave now, matter wave.
Yeah.
So
Yeah.
de Broglie's nonsense should apply.
Yeah.
So lambda squared should become lambda, which is equal to h by mv squared.
That's why I square. Yes.
So it works out as h by v whole square multiplied by psi. So I'll
Hmm.
be having del square psi working out as minus 4 pi squared by h squared into m square v square. So I can write as m into mv squared.
Yes, sir. Energy.
Correct? Mv squared is what?
Kinetic energy.
Kinetic energy. But is it
2 into
kinetic
kinetic
energy or
energy.
twice kinetic energy?
2 into kinetic energy.
2 times kinetic energy. So this works out as minus 8 pi square m by h squared into kinetic energy into psi. Kinetic energy is what? Total energy minus potential energy.
Yes, sir.
So I'll write this as del square psi now is equal to minus 8 pi square m by h squared into E minus V. E is my total energy, V is my potential energy multiplied by psi. This is your final form of Schrödinger's equation.
Yeah. Okay.
You understand the idea here? So Schrödinger's equation is nothing but the standing wave equation extrapolated to 3 dimensions. So what the hell did he solve for? He solved for psi of x comma y comma z.
But then why can, like, they say that we can only solve for like s orbital or something like that.
No. Schrödinger has solved for all of the individual pieces. What is an orbital? What did I describe to you? What is the thought experiment which you are told to think along as the case study here? You are the wave,
Yeah. Yes.
and your entire COVID period is basically shot into a 2-minute time span. You are the wave. If I want to study this wave, it is too complicated, correct? The equation is too complicated. I can't study it in a proper manner because the equation is different in different parts.
Yeah.
Right? So in your room, you are going to be in a particular place in a particular manner only. In the dining table, you're not going to be lying down. You're not going to be pissing on the dining table. You're going to be only sitting there, or you're going to be standing next to it. Right? There are only certain ways in which the way which is you will be behaving there. Yes or no?
Yes, sir.
So the idea here is you're going to be looking at this particular wave in a way in which you break down the space inside which you're studying. The atom now is your entire house.
Yeah.
You are bound in the space called your house.
Yes.
By whatever attractive force, I don't give a shit there. But the reality is you're bound in that space. You behave differently in different rooms.
Yeah.
And in different rooms, in different parts, you behave differently. At different times of the day, you'll behave differently.
Yeah.
Right?
Yeah.
That's basically what we're doing here. So what did Schrödinger do? When you talk about a particular subshell or a particular orbital, what does that mean? A particular location inside the space called the atom, you're trying to find the equation of the electron, how it is going to be behaving.
Okay. So,
you understand the idea?
Yes, sir. Yeah.
What is the problem there? The problem is this. When you are one individual in one building, it is easier to basically identify what your behavior is going to be. You can predict it reasonably well. But if there are two individuals, what happens? They will interact with each other.
Yes.
Predictions become much more complicated.
Yeah.
That is why we can't predict when there is more than one electron. You understand the principle over here? So we can basically do Schrödinger's also for only one electron species. It is solved only for single electron species. What does solved mean? He found out the equation, that's all. He doesn't understand shit beyond that. Mathematically, what is the equation? He knows. So if there is one person in a prison-like environment called an atom, a big building, massive prison called the atom, how will they behave inside that space called the atom? How is their behavior? How do you study it? You basically break down the space called the atom into pieces, into different rooms, and in those different rooms into different locations.
Yeah.
And in each room you study, in each location you study, what is going to be the mathematical equation for that species called the electron.
Okay.
The mathematical equation by itself gives no meaning. But if you take psi squared of that mathematical equation and you study that, that has some physical meaning. The physical meaning is going to be what is the probability of finding the electron in that spot.
Okay. So then for a standing wave, if you square that f of x, will that also give you a probability?
No, I have no idea about that.
Okay.
Do not assume that I know the physics beyond a point. I know the physics which is going to be connecting here sufficiently. I do not know beyond that level there.
Mm-hmm.
You understand how Schrodinger's works now?
So why exactly does the psi square give you a probability density?
No idea.
Okay. Okay.
Now, how is it studied? Schrodinger basically derived psi of x comma y comma z. The equations, we have no idea how to use them. They're very complicated. So he
Mm-hmm.
solved it and he got the Nobel Prize. The next shit came to understanding them and how to meaningfully pass down the knowledge. So that is where Hamilton comes in. I'm assuming you have learned about something called the Hamiltonian operator.
Ah, yes. Yeah.
So what this bugger did was he converted this psi of x comma y comma z, which Schrodinger solved for, which was in Cartesian coordinates, into what is more
The
easier to understand for us, which is
RT.
spherical polar coordinates.
Yeah.
Why is this easier to understand for us? Because if you write the psi of x comma y comma z in this form of psi of r comma theta comma phi,
Lot of
you
cancellation.
can break this down into a new manner here. Psi
Hmm.
of r comma theta comma phi can now be written as r of r multiplied by a of theta comma phi. Basically, you can write this one big equation called the electron now into two separate parts.
Hmm.
One which is going to
Factorizing.
be an r of r part, another which is going to be an a of theta comma phi part.
So factorizing. Okay.
Yes, you are factorizing it exactly.
Hmm.
So this is called as a radial part,
Oh, that's why. Oh,
and
okay.
this is called the angular part.
Hmm.
Now, what does the radial part tell you? The radial part is going to be the mathematical part of the equation, which is going to be doing, or which is going to be involving anything and everything from, which is going to be talking about only one variable, the distance of
Distance.
electron from
Okay.
the nucleus.
Hmm.
Whereas the angular, so this is going to be covering distance of electron from nucleus.
Okay.
What should the angular then cover?
The angular position.
What does that mean?
The
Direction.
direction exactly. Yeah. Hmm. It's like
Direction of electron from
hmm.
nucleus. Now, obviously, even the r of r and a of theta comma phi are massive equations by themselves. So we cannot remember those equations. What
Okay.
can we remember out of them?
Can be broken down. Hmm.
So we remember the graph for r of r. So when you are plotting, say, psi versus r or psi squared versus r, you know
Hmm.
these graphs,
Yeah. Psi
right?
square. 4 pi. Yeah.
And you know also psi square, or the not really psi squared, you also know
4 pi r
4 pi
square.
r square psi square
Yeah.
versus r. You know these three graphs, correct?
Yes. Sir.
What
Hmm.
are you really plotting there? You are plotting, instead of psi, you are not plotting psi, you are plotting r of r versus r.
Okay. So we're not. Okay.
You're not
Yeah.
plotting the entire thing, you're
Yeah.
only plotting the radial component.
Hmm.
Same way, when you're plotting psi squared, you are actually plotting capital R squared of r versus r.
Maybe that's why. Okay.
And the graphs, the shapes are all you remember,
Ah, yeah. That's
right?
yeah. Yes, sir.
Because those shapes tell you where you're going to be having a node and not a node, where you're going to be having a peak, etc. etc.
Hmm.
Basically, this is all you are learning. 4 pi r square psi square. Now, what are you really doing? You're plotting 4 pi r squared into capital R square
Yeah.
of r.
Yeah.
So, what this gives you is when you're multiplying by 4 pi r squared, that means you're taking
Yeah.
the
That.
entire sphere of points on the surface over there of the sphere, all of those points.
Ah. Yes.
4 pi r square stands for what? Surface area
Hmm. The shell.
of a shell or of the sphere of radius smaller.
Hmm. Yeah.
So, what you're calculating there is the total probability density or
That
total
enclosed
chance
region.
of finding an electron at a distance r from the nucleus.
Hmm. Okay.
This r squared of r, you're going to be calculating not the total chance here. You're calculating here the chance of finding an electron at that particular distance r from the nucleus. This is going to be average. This is total.
Average. Average total.
This average across all directions.
Hmm. Total across all directions.
Yes, total across all directions.
Yeah, yeah, okay. Hmm. Hmm.
You also learn a squared of theta comma phi, the graphs for these. What
Oh,
do you think these are? I'm telling you, you know this. What are these? You know them
angular
by
lines.
different name though.
Set.
You know them by a different name.
Um, so we, oh,
The plots of a square of theta comma phi are basically the different shapes of the orbitals. S orbital is a spherical shit. P is going to be this dumbbell. How do you get that shit? What does that mean? That is basically plots of a square comma of theta comma phi.
oh, okay, okay, okay. Yeah. Huh. Yes, sir.
You understand the idea?
Yeah.
So you learn two types of graphs actually. One is radial graphs, another is angular graphs. We don't call it that way though, but that's what you're learning. Because
So
we
then if
can't
you,
remember the exact mathematical functions. They're too complicated. What we know is we can remember the easier part of the solution. That is what we are memorizing. That
sir,
is what. Hmm.
if you have R of R and A of theta and all this, why can't you get psi?
You tell me, is it going to be still that simple?
I mean, it won't be, but then we can do it, right?
Let me ask you a very simple question.
I
Draw
mean,
the shape of 3s orbital. Shape of the 3s orbital. How will it be?
spherical.
Spherical, yes.
Yeah.
No doubt about that.
But
But
then there'll be gaps inside, and then
you're getting the
yeah.
point now, no? So 1s is going to be this guy. Then there will
Then
be
a
a gap
P
between.
as a two.
And then you'll have your 2s and so on and so forth. I think you start getting the basic problem over here, which will be coming up.
Hmm.
Right. So the
Sir,
gaps, what are those gaps? Those are the radial nodes,
radial nodes. Yeah.
right?
Hmm.
So just for the 3s, it is that complicated.
Hmm. P and all that bit.
Yes. You understand why we break them down into pieces, and because the individual data, when you keep collecting it together, now it gets too complicated.
Hmm.
We cannot simply understand shit out of it. So we break it down. We break it down and we learn it.
Okay.
You understand the idea here?
Yes, sir. Yeah.
Okay. Okay, we will just discuss a couple of questions and I'll shut it.
Oh, yes, sir.
Okay. All right. लंच के लिए टाइम हो रहा है क्या?
Yeah, kind of.
Okay, fair enough. We'll discuss these two questions and we'll call it quits.
Okay, sir. Yeah.
Quickly have a look at these two. So first one, the standard heat of formation listed for gaseous ammonia is given over here. And at the constant pressure, heat capacities of these gases are given over here like this. Determine the enthalpy change of the reaction at these two conditions over here, respectively. Okay. So in this particular case here, they're giving you standard heat of formation of ammonia is given, and that the constant pressure heat capacities of the gaseous species over here, heat capacities at constant pressure, now they're giving you CP values.
Hmm.
Okay.
Yeah.
At different temperatures over here, at different for the different gases over here. So the idea here is you're going to be having in this case here the standard heat of formation for gaseous ammonia is going to be listed as -11 at 298 Kelvin. So that is going to be this value. This is going to be given as -11 kilocalories per mole.
Yeah.
Okay. And this is going to be what is asked over here at a different temperature. Right.
Hmm.
So for the same reaction of formation of ammonia at a different temperature, if I want what is going to be the enthalpy change for that reaction, how to proceed over there is like this. First, write the equation.
Okay. Okay,
Formation
I
actually
think,
1 mole of this guy being formed.
yeah. So 1/2, 3/2. Sir, can
Oh,
I try this one?
okay.
Actually, fine. I'll just.
No, it's okay. It's okay. There's an equation which is called the Clapeyron equation. You're familiar with that equation?
So I don't remember it. I've heard of it.
So it is an equation referred to as the Clapeyron equation. This is based on that.
Oh, okay.
The reason why I picked this question was so that you get introduced to that equation. I thought you would already have the equation in your school anyway. Looks like they'll not discuss that equation. So let me quickly introduce how that goes here.
Sir,
All right,
can't we do this like manually?
let's do this. I'll leave this question for you to think on. We will discuss the second one first. So
Okay.
calculate the resonance energy of isoprene from the data given. Isoprene is going to be given as something which has formula as C5H8.
Cyclo.
Not necessarily cyclo, do
Okay.
not assume cyclo.
Okay.
Now, standard heats of combustion of isoprene, carbon and hydrogen are given here.
Hmm.
So they're giving it to you as heats of combustion. So C5H8 plus O2. Whenever
Hmm.
you're given data, what is your first job? Put them down.
Balance. Oh,
Put them down properly. Put them down
yeah.
equation form wise.
Yeah, that's
So standard heat of combustion now for combustion means it's defined for what? For 1 mole of the substance being
CO2. Complete.
put 1 mole of this guy being burnt. I'm going to be getting complete combustion products as of course carbon dioxide and water.
Hmm.
So how many moles of carbon
5
dioxide?
carbon
5
should be there.
moles. Water, 4.
Water 4. Yes, 4.
Right? So we're going to be
4
having
this
5
side, 10
plus
this
6 is
side,
7.
7. Yeah.
This is the equation.
Yes, sir. Yeah.
Next up, they are giving standard heat of combustion of carbon. Carbon being burnt, 1 mole being burnt is
1
basically
mole of CO2.
the formation of carbon dioxide.
Hmm.
That is, we can write it as enthalpy of combustion of carbon is the same as enthalpy of formation of carbon dioxide.
Yeah. Oh, correct.
Yes or no?
Yes.
Same way for hydrogen, H2 plus O2 giving H2O.
Hmm.
I can write enthalpy of combustion.
Is equal to formation of H2.
Hydrogen gas is same as enthalpy of formation of what?
H2
Water.
is equal to sigma bond. Okay. Hmm.
Correct?
Yeah.
Now, they are giving us bond energies of C double bond C, C single bond C, C single bond H, and H single bond H. And they are
Hmm.
giving standard heat of sublimation of graphite.
Yeah.
Okay. Now, let us now try to see how to basically get this done here. So this is going to be heat of sublimation of graphite is given to us, and they are giving us H single bond H bond also.
Yes.
Okay. So now let us try to see how to form C5H8. If I have to form C5H8, let's look at what should be C5H8 roughly. If it is C5, what is the general molecular formula telling you it should have if it is fully saturated?
6 minus 1 ring, 1 double bond, 2 double bonds, 2 ring.
2n plus 2 Cn H2n plus 2 is full saturated.
Ah, yes.
So
Yeah.
it should have been C5H12.
Yeah.
Instead of 12, I'm having it as what? 12 minus 4.
Okay. Hmm.
Correct?
Yeah.
So double bond equivalent is how much?
It's
2.
4, 2. So 2.
2.
C plus. Hmm.
So I do not know what is present, whether it's a double bond or a triple bond, but I can guess how many double bonds should be there.
Yeah.
2 double bonds should be there.
2 pi pi.
Remaining all should be single bonds over here, correct?
Yes, sir. Yeah.
So C5H8 or isoprene.
2 moles of H2.
So
Oh,
should be having 2 C double bond C,
yeah.
correct? So let me randomly draw one possible structure and see what is the scenario there.
Okay. So we need to break 2 pi bonds.
So this is going to be the expected formula here, which will look like this. CH three of these,
Hmm.
one hydrogen, one hydrogen, one hydrogen, and two of them. Correct? 1, 2, 3, 4, 5, 6, 7, 8.
Yeah.
This could be it.
or a triple bond also. Yeah.
No, 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 it doesn't matter what it is. They have given me only for double bonds here. Or they may be in 1 and 5. Instead of 1 and
That's
4, 1 and 3, now it can be 1 and 4.
yes. Right.
Correct? Huh?
Yes. Yeah.
I can put it at 1 and, or it can be some other form of.
Anything. Yeah.
The methyl could be somewhere else. I don't know where it is.
Hmm.
Right? So if it is of this kind over here, it is going to be having what bonds present here? The number of bonds present will be remaining the same as long
Yes.
as double bond equivalent is same. Correct? So
Yeah.
I can say 2 carbon double bond. How many carbon single bonds are there?
Carbon single bond. 5.
Double bond na C, double bond C together.
Oh, so we're not. Oh, okay, man.
Hmm.
Then 2.
2. Then how many other bonds are there? 8 carbon sigma bond
CH.
hydrogen.
Yes, sir. That's it.
Correct?
Yeah.
These are the bonds which are formed when you're forming 1 mole of isoprene. Correct?
Yeah.
So now let's write an enthalpy of formation of isoprene. I'm going to be having carbon solid plus hydrogen gas, giving me C5H8. Correct? 1 mole of this fellow.
Yeah.
Let's not bother with what physical state this guy is. Let's assume it's formed whatever. So what are the processes I should be doing here? I should first convert the carbon solid into carbon graphite.
Okay.
And I should break the
Break the
hydrogen
hydrogen.
into hydrogen atoms.
So should we balances?
We will balance, but
Okay.
let's look at the process, then we'll combine them all. So first, 1 mole
Breaking
of
of bonds.
5 carbon and 4.
Yeah.
So 5 moles of carbon solid should have been made into 5 moles of carbon gas.
Yeah. 4 moles of
4
H2, 8 moles of
molecule should have been made into 8 moles of hydrogen atom.
H. Now we should combine them.
Now we should combine these guys and get here.
Okay. Yes, yeah.
Now this process is going to be sublimation.
Yeah, the 5 and 2, the given.
And this is something where I am breaking what? H single bond H.
4.
Correct?
Yes, sir.
And what am I forming here?
2 sigma, 2 CC. Yeah.
2 C double bond C,
2
2 C single
CC.
bond C, and 8 C single bond
CH.
H. Now they have given us values for this.
What did they ask?
They're asking resonance energy, if any, for C5H8.
Okay.
So you need to calculate this enthalpy of formation
Subtract
in 2
by.
different ways.
But no.
Calm down. Pay attention here. In this here, you can calculate enthalpy of formation now. How is that going to be? First, I need to take this process.
Reactant minus
The value for this. Can you calculate the value for this?
Yeah.
Done. This, can you calculate the value?
Yes. Yes.
Done.
Subtract.
This is given.
Yes.
This is given. This is given. That means I can find this out.
Yes.
By adding and subtracting. So let's substitute the values and check out ki kya aa raha hai. Let me just simply put the values over here. Sublimation of graphite is given as 718.3. So this is 5 times 718.3.
Yeah.
So let's put down the numbers. So delta H formation of C5H8 is going to be 5 into 718.3.
Plus 4 into.
No, stop. Don't do that. That is for a calculator to be done later. Now next, what is going to be the next thing? 4 into, sorry, you're doing that only. I'm sorry. Sorry. 4 into what?
4 into HH. 438.8. 435.8, my bad.
So it's going to be plus 4 into 435.8.
Subtracted by.
Next.
2 into C11C.
2 into 615.
Plus.
So minus 2 into 615.
Minus again 2 into 413. No, 413.
348.
348.
Those are
Sorry.
important. You have to take those data out carefully and put them down.
Yeah.
Minus
Plus 8
8.
into
Don't have the book over here, so yeah, fair enough. CH
CH. Third one. 413.
413.
104.7.
This is going to be enthalpy of formation of C5H8 expected.
Yeah. But they give the value.
Expected, no resonance.
Yeah.
Correct?
Yes, sir. Yeah.
Now, you can calculate enthalpy of formation of C5H8 using this also.
Hmm.
In this approach here, how do you calculate here? You've been given enthalpy of combustion of this. I mean, enthalpy of formation of this, enthalpy of formation of this.
Yes.
Right? You've been given enthalpy of combustion of
We
this
can
also.
get it from this route.
Right?
Yeah.
So, calculate enthalpy of formation from this.
Subtract by
So,
this.
we can write it as enthalpy of combustion of C5H8 is equal to formation of products minus reactants, correct?
Hmm.
What are the products form? 5 moles of CO2, 4 moles of H2O.
Yeah.
So it is going to be 5 into enthalpy of formation of CO2 plus 4 into enthalpy of formation of H2O minus 1 reactants. I have to subtract enthalpy of formation, correct?
Hmm.
This is something which I do not know as of now, so I'll put it as enthalpy of formation of that guy. This is how much enthalpy of formation?
7 into the we have
normal elemental form already. So 0.
0. Yeah.
So minus 1 into enthalpy of formation of C5H8. This is enthalpy of formation actual,
Yeah.
including resonance.
We have this value. Yes. Now we can calculate.
So with resonance.
Okay.
You understand the idea now? So you calculate this value from here and you compare it with this value which you have calculated here. The difference between them will give you your resonance.
Yeah. Okay. Understood. So, yeah.
You understand this type of a question?
Yes.
This is a typical good question, which you can expect as what to say, a middle level or an easy level JEE advanced question. I would call it a stage category 1 or category 2 JEE advanced question. Which it is not exactly category 1, but it's a category 2 JEE advanced question. Where we have some time, and if you have practiced this kind of a question before, you can definitely try it out and get it correct if you are patiently doing it. It doesn't involve too much thinking, so you can say it's category 2, category 3. Not really beyond that.
Yeah.
It doesn't require special level thinking and shit. It requires regular thinking. You understood this question properly?
Yes, sir.
Now, we'll close the session here. You think on this thing for yourself.
Yes, sir.
This is something which is going to be requiring a new equation. You think.
Okay. Wait, so we cannot do it without the equation?
No, you can.
Okay.
Can.
Okay.
You can derive the equation and do the same thing. It's not that complicated of an equation. It's a fairly straightforward shit only. So
Okay.
it's not going to be that complicated. You have to understand though a little bit more. Let's see where you come. So
Okay.
you have done physics. So this will test how well you understood physics.
Okay.
Okay. So I'll quickly describe what we are trying to do here. We are given the enthalpy change. We are given the enthalpy change for this reaction. Given delta H naught for the reaction at 298 Kelvin. Asked to find delta H of the reaction at 773 Kelvin. So all the substances, the reactants, products, all of them are scaling up in temperature. All of them are gases, and it's all done at constant pressure.
Yeah.
That's the hint I'll give you. You have been given the CP values for each of them.
Okay.
Okay.
Yeah.
All right. I will close the session here. I'll see you sometime tomorrow or day after. Practice some more. And thermodynamics, please sit and practice enthalpy related questions. I did not ask you to sit and do work done.
No.
Okay, sit and practice enthalpy related shit because we have discussed a bunch of enthalpy related shit already. Please start practicing enthalpy related questions. They are going to be very critical. That is where your chemistry questions will come from,
Okay,
mainly,
sir.
not from Carnot and shit.
Oh, okay. Hmm.
You've been
Hmm.
Carnot and crap.
Let's skip that.
That's all physics crap. Don't go there. Work done. If they're asking for irreversible processes, yes, that's chemistry. If they're doing reversible only, that's the same as physics.
Hmm. Okay. Yeah.
All right, let's close it here today.
Yes, sir.
I'll
Yeah.
see you some other time next time. Bye bye.
So yeah. Thank you, sir. Have a nice day.
Have a nice day. Bye bye.
Nice.